And sometimes what happens if you have complex poles also, this method is going to work. So you know that because B1 is going to be sum of the time constant. So when the complex numbers, when you add the complex poles, you know complex poles will always come in pair. So when you add the complex pole, the imaginary part will get cancelled. So however, complex poles also will be considered in the system. You need not worry because B1 is sum of all the poles time constant. So the negative part, imaginary part is going to be cancelled out, which will ensure that the coefficient B1 is going to be completely a real number. And however, when you consider two-pole system, it depends on both the real and imaginary parts also. Okay. Generally, we cannot say by seeing a network if the complex poles are going to be an issue in estimating the bandwidth. But I again say we have to identify what components are present in the circuit first, list out them, and then only you can clearly say what is going to be the estimate of my bandwidth. Okay. So without seeing the network, it is going to be very, very difficult to estimate bandwidth because you never know what is inside the network. An important idea is not all capacitors belong to OC calculations. Very, very important. You will not consider all the capacitors in open circuit time constant calculation, because it depends on finding the equivalent resistance. You are going to open out all the capacitors. So across that resistance, equivalent resistance, what all capacitors are available, only those will be considered for finding out the OC tau estimate. So blind application of OC tau will lead to conclude erroneous values of bandwidth. So blindly, if you apply OC tau method for any network, you may get a wrong estimate of the value. Actual circuit behavior, only if you find the actual circuit behavior by exciting the circuit and finding out the mathematical values, you can actually estimate the real bandwidth of your system. So far we have considered the system to be having all poles only. We didn't consider any zeros at all. If there are going to be zeros, then the estimates may be wrong. So this OC time constant is predominantly applicable to networks having all poles and no zeros. If zeros are also there, then our model may give you the wrong estimate also. That is what to say emphasized here. And we state this OC tau are more concerned with R and C only and not with inductors. If your circuit has inductors, you may not consider that for the bandwidth estimation. We consider only R and C. So exciting the network at high frequency, when you excite at high frequency, what will happen to the gain if the capacitor is going to be open circuit? That's what we are doing, right? So for finding the effective time constant, we open circuit all the capacitance and we find out RJ naught. RJ naught is going to be the effective resistance. And one issue in high frequency is when you excite at high frequency, the parasitic effect will be there, and these capacitors will actually be short circuited. But theory wise, we say that the capacitors are open circuited. So that is one contradictory assumption what we make. So that is why they say whatever estimate you are going to get by this method, you don't worry about the estimate, just keep it as a reference. And you do the experiment and plot the frequency response graph and estimate the bandwidth for your actual network. So if the gain does not change upon removing the capacitor, then the capacitor should be probably short circuited. So that is the thing. Even after opening or shorting the capacitor, the gain is not reducing by so much, then you can assume that the capacitor is not going to play a role, and that you can use the capacitor for calculation. So number of time constants may be unequal. So you cannot clearly expect each time constant to be each OC tau to be equal to the time constant. So OC tau is going to be sum of all the time constants of all the RC components. So it is not equal to 1 RC. It is going to be summation I is equal to 1 to n tau n tau I.